The pursuit of artificial intelligence is the effort to simulate human cognitive functions inside a machine, giving a computer the ability to reason, solve problems, and perceive its physical environment. Within that broad pursuit is machine learning. Instead of relying on hard-coded instructions, this subset uses statistical algorithms to make decisions. By feeding these algorithms historical data, the system identifies patterns and improves its own performance, grouping inputs without explicit programming. This approach is highly effective for many applications, but its utility is strictly bounded by the structural complexity of the data you feed it. Defining the exact boundaries between these concepts is a matter of practical engineering. The problem you are trying to solve dictates the mathematical architecture required to process the data. Traditional machine learning algorithms excel when processing structured datasets, like tabular financial records or organized CSV files. Processing this data requires a human-led step called feature extraction. Engineers must manually isolate the relevant variables, such as an applicant's income or credit history, before handing that information to the algorithm. But the physical world rarely provides neatly organized spreadsheets. Images, audio streams, and natural language represent unstructured data, where variables are buried within chaotic environments. A human engineer cannot manually isolate and write a mathematical definition for a pedestrian or a traffic light from a raw array of millions of shifting pixels. This limitation in handling dense, unstructured inputs forces a shift in architecture toward deep learning. By utilizing multi-layered neural networks, the system moves past human-guided feature selection and begins performing automated mathematical feature discovery on its own. If a hospital wants to predict patient risk, a traditional statistical algorithm can easily process a structured database of ages, blood pressures, and existing conditions. That same algorithm cannot evaluate a high-resolution X-ray or MRI scan to locate a medical anomaly. A tumor does not exist as a discrete numerical column. It is a complex spatial pattern composed of subtle variations in pixel intensity across a visual matrix. Deep learning bypasses the need for manual feature extraction by deploying artificial neural networks that ingest and interpret the raw pixel matrix directly. The mathematical architecture of deep networks provides the specific capacity to perceive patterns in data too dense and disorganized for traditional statistics to process. The foundational computational unit of these networks is the single artificial neuron, derived from the Macaulay-Pitts model. Processing begins with an input vector, representing the raw data flowing into the node, such as individual pixel values from an image. Inside the node, each input is multiplied by a specific weight, and an additional value called a bias is added. These parameters determine how much importance the network assigns to each incoming piece of data. Simply summing these weighted inputs results in a linear transformation. If the network stopped there, it would be incapable of mapping the complex realities of the physical world. To solve this, the node passes its final sum through an activation function. This mathematical threshold introduces nonlinearity to the output. Without activation functions, the entire architecture of a multi-layered deep neural network would mathematically collapse into a basic, single-layer linear regression model. This chart illustrates the sigmoid activation function. Historically, engineers used this formula to compress network outputs into a strict probability range between 0 and 1. Looking at the derivative graph on the right, the curve peaks at 0.25 and quickly tapers off towards 0 at the extremes. During the backward propagation of errors, this causes the learning process to stall, a limitation known as the vanishing gradient problem. To maintain gradient flow in deep architectures, modern networks typically use the rectified linear unit, or ReLU. ReLU simply outputs the maximum of 0 or the input value. By returning a constant gradient of 1 for all positive inputs, it prevents the gradient from vanishing and enables highly efficient weight updating. However, this efficiency introduces a specific vulnerability. If a negative input causes the derivative to drop to 0, the neuron dies and permanently stops updating its weights. Despite the risk of dead neurons, the system utilizes backpropagation, applying the chain rule of calculus to continuously calculate errors and adjust the network's internal parameters. The precise mathematical function selected for these nodes dictates whether a network successfully maps high-dimensional data or mathematically stalls out during the training phase. When millions of these individual nodes are stacked into a complete deep neural network, the input layer passes raw data into a sequence of hidden layers. The first hidden layer processes the raw pixels to isolate basic structural edges and gradients. The second layer takes those isolated edges and combines them to identify complex shapes and distinct visual textures. The deepest layers synthesize these shapes into the recognizable, abstract form of a tumor before reaching the output node. This process is called hierarchical abstraction. It requires no human intervention. It occurs entirely automatically as the network uses backpropagation to optimize its own weights. By stacking layers of non-linear transformations, deep learning successfully parses the unstructured data that paralyzes traditional statistical models. Moving from mathematical theory to real-world deployment reveals a steep hardware cost. Traditional machine learning algorithms execute efficiently on standard CPUs, but deep networks demand a vastly different physical architecture. Training a deep model requires processing millions or sometimes billions of parameters simultaneously. This level of parallel computation specifically requires graphics processing units, or tensor processing units. Alongside specialized processors, deep networks must ingest massive volumes of labeled, unstructured data across thousands of training cycles before their weights accurately converge. While this architecture offers superhuman perception, the extreme dependency on high-performance compute clusters and massive datasets creates a severe barrier to entry compared to traditional structured learning models. Beyond hardware costs, the architecture introduces a critical structural limitation, a severe lack of model interpretability. When a traditional algorithm, like a decision tree, denies a bank loan, a human auditor can trace the logic step by step and identify exactly which variable triggered the rejection. In a deep neural network, features are extracted automatically across millions of hidden parameters. The specific logic path the network uses to reach its conclusion is obscured from human operators. This creates the so-called black box problem. The inability to explain an AI's decision-making process becomes a critical liability when deploying these systems into high-stakes environments like medicine, law, and autonomous driving. The taxonomy of computational intelligence is clear. Artificial intelligence provides the overarching goal. Machine learning supplies the statistical tools to evaluate structured data, and deep learning provides the neural architecture required to perceive the unstructured world. Advancing the field requires a departure from simple hardware scaling